Okay, so before we start an example and illustrate how the method works, let's discuss a little bit which type of physical situations require such non-homogeneous terms. So here's an example of a heat equation which is not homogeneous. So let's actually review briefly what the homogeneous equation means. Remember, that means you have in the PDE a term that doesn't depend on the dependent variable, which in my case it's U, right? I mean, as usual, the dependent variable denoting the temperature at location X and time T. So remember, a quick check to see if it's homogeneous or not, replace all the U's and its derivatives with zero. If there's anything left, then that's going to be the non-homogeneous term. So what makes it different than the previous examples of non-homogeneous equations we solved is the presence of something that depends on T rather than X only. So this example, we can call it, as I mentioned here in the title, a heat equation with internally generated heat, gain or loss, because this could be a possible interpretation of this term. So remember, if you have a homogeneous equation, so if you don't have this guy here, then that describes how the heat flows in a horizontal rod. When the heat flows from left to right, depending on, after you prescribe what happens at the boundaries. So again, for a homogeneous equation, if you only have this, ut equals uxx, that equation models what happens with the heat flow in the rod given a prescribed situation at the boundary, either prescribed temperatures or prescribed heat flows, insolation or some specified heat flux to the right or to the left at the boundary points. So you specify what happens at the boundary points, and then you let the process go, and you model with that equation how the temperature changes in the rod. On the other hand, due to, for example, chemical reactions in the rod itself, you may have some heat energy gain or loss that changes in time. Chemical reactions are the easiest thing to imagine, right? I mean, in addition to the heat that comes from the boundary points, you could have internally generated heat that may depend not only just on the location on the bar, but on the time itself. So as time goes on, you may have some increase in the temperature or some decrease in the heat energy, to be more precise, because of some internal reaction in the rod. Another example could be, for instance, a nuclear fuel rod. So that is the justification why this may depend on T, right? So this term here could be internally generated heat gain or loss. I'm going to call it gain or loss because, the overall sign of this quantity could be positive or negative. And I want to emphasize that the way we dealt with the non-homogeneous equation before doesn't work in this case because of this T, because of this explicit term that depends on T. So remember that in the previous cases of non-homogeneous equations, you would take, you will make a substitution. In other words, you would write your original dependent variable in terms of a new dependent variable, big U of xt, plus some function of x only. So that would work in that case because you could pass the non-homogeneous terms, if you remember, to h of x. Again, provided that the non-homogeneous terms were dependent on x only. So if that were the case, I mean, if I try to do the same thing here, if I plug in this quantity into the PDE, when I take partial t, h disappears, of course, and you have big U partial t. And on the right-hand side, little uxx is going to be big U xx plus h double prime of x plus the non-homogeneous term. But the goal, remember, was to create a homogeneous equation in big U. And that would have worked if I could determine the function h double prime of x such that this guy is 0. But of course, that basically goes against our main assumption, namely that h depends on x only. So because it depends on t, we cannot obviously figure out such, there is no such h of x. So that trick again with the substitution only works insofar you could have this type of translation, if you want, between or a summation between a function of x and t and a function of x only. And then if you can determine that function little h, which will cause you to have a homogeneous problem in big U, then the method works. But of course, h in this setting cannot depend just on x, because unfortunately, your non-homogeneous problem depends on t as well, or the non-homogeneous term depends on t as well. So pause for a moment. You may want to look at some previous example with this method to realize why that doesn't apply. It's important to take a moment because, as you will see in the later lectures, when we put all these things together, these type of methods can be used in conjunction with others. So for example, you could still use this to handle possible non-homogeneous conditions in the boundary condition. So we could still use this one, but then when we move on to this this term here, we have to handle it with a different method, which is the one I'm going to present today. So the so-called method of variation of parameters. So how does that work? Oh, we forgot the boundary conditions, right? So before we move on, let's put some boundary conditions in the heat equation. And by the way, notice that I chose here to have coefficient 1 just to make it as clean as possible in the beginning. So let's put some Dirichlet conditions on the boundary. So u of 0t equals u of pi t equals 0. So we have 0 temperature at the boundaries. And then some initial temperature distribution, let's say u of x0 equals x. And just so you know, because you notice that I keep on using x as a possible function to begin with for the temperature, this is because I like to have easy examples since in the beginning, because this function x and also pi minus x will have easy Fourier series. So the Fourier series have more compact coefficients, and it's okay to have as a first example a clean example as much as possible, because these problems are long anyway. So, but remember, any function will do here in terms of x, as long as you can produce the Fourier series that you will need at the end. So with that being said, the method of variation of parameters deals with the way to handle the problem is in the following way. You look first at the homogeneous part of the equation and analyze it. So analyze the homogeneous part. It's not like you have to solve it completely. You will see immediately what I mean. Just analyze the homogeneous part and figure out the Sturm-Liouville problem, the eigenvalues, and the eigenfunctions that result from this. In particular, the eigenfunctions will be the ones that are important, basically. So if I were to solve the homogeneous part, you can take the time to do all the details, but at this point, let's just state it right away, because we met this before. The Sturm-Liouville problem is going to be x double prime plus lambda x equals 0 with the boundary condition x of 0, x of pi equals 0. And we know already that the eigenvalues are lambda n equals n squared on the interval 0 pi, of course, and the eigenfunctions are sine of nx. Furthermore, the equation in t, again, if you proceed with the separation of variables, is going to be t prime plus lambda t equals 0. And you solve this for every eigenvalue. Again, I'm going to go a little bit faster on this one because we met this type of problem before. So if it looks like new to you, again, pause and do the extra steps when you separate this and figure out that you do indeed end up with this equation. And When you solve for t, and again the solution is labeled Tn of t, you will get an e to the minus n squared t. So if you were to solve the homogeneous part of the equation, your solution would be summation from 1 to infinity, some constant an, e to the minus n squared t, sine of nx. So you'll see later you don't have to do actually all of that stuff. The only thing you need to do actually is to come up with the eigenfunctions, and then you will determine the coefficients of the eigenfunctions in the solution by a different mean. But for a moment, let's pause for a second. And again, look at the solution you would get if you were to have a homogeneous problem. So once again, this is not the solution of the original. I just determined the solution of the homogeneous part to illustrate how the method works in handling the real problem that we have over here. So the method of variation of parameters says the following. Why don't we assume that the solution still is a series in these eigenfunctions, but with different coefficients that I might be able to determine by different means? The reason such an assumption may work is because if you look carefully here, if I were to plug in such a series over here on the left side, and in the place of uxx, you end up with summations of sine of nx, right? Because if I differentiate, so on the left of the equation, when I do partial t, this is not affected. Sine of nx still remains on the left. When I plug it into this term, when you do partial x twice, you end up with sine of nx again, with some other extra coefficients because of the chain rule, but it's still sine of nx. And this part here, pi minus x, this coefficient, I can get it in terms of sine of nx just by looking at the Fourier series for it. So presumably, I'm going to have essentially an equality of summations in sine of nx. The only question is to find some magic coefficient in t that somehow matches e to the t. So basically, that's the insight of the method. You don't have to anticipate how it works because it will be obvious as we go along the way. But this is how the main idea works essentially in the variation of parameters. So now we come to the main step in the variation of parameters method. Once you determine the eigenfunctions of the homogeneous part, take a solution or look for a solution of the original problem in the form of a series of sine of nx with coefficients in t yet to be determined. So let's call these coefficients bn of t. Okay, so after you hear what I'm saying right now, you can again pause and maybe rewind to make sure you guys understand what I'm talking about. So variation of parameters, as the name implies, you look at that coefficient, you let it vary with respect to t, and that becomes now an unknown function in t. And now the question is, how can I determine this bn of t such that this summation becomes a solution of the original problem? So look for a solution of the original problem in the form of a summation of sine of nx. So in a nutshell, basically, to summarize even more what we just did, you look at the homogeneous part of the equation. You identify its eigenfunctions. The eigenvalues are less important at this point, but the eigenfunctions. And then you look for a solution in the form of a series of those eigenfunctions with coefficients in terms of t yet to be determined. So without further ado, let's see how we determine these coefficients. And to make it, let's see, more easy, to make it easier to follow, let's actually copy again the problem on the next page. Let's do another part. So we're gonna copy the problem. I'm gonna copy this, and then we're gonna proceed with plugging in this format and solving, illustrating the method. So stay tuned for the third part.